In this lesson, I'd like to run through the life cycle of a star. As you've probably heard, the lifespan of a star is extremely long. We're talking about not hundreds or thousands, but billions of years. So how exactly is a star born? Well, astronomers believe that all stars form inside something called a nebula. It's basically the nursery of stars. Fancy way of saying it. It's also probably the remnant of a dead star from before. But there is a huge cloud of dust and gases, and what happens is this dust and gas energy somehow makes it begin to spin. When it begins to spin, that increases the pressure, the squeezing of the gases, so that eventually the temperature increases. And when that happens, because of the increase in pressure and the increase in temperature, something called nuclear fusion starts. And that's basically when the hydrogen gas takes 4 of these hydrogen atoms, will fuse together to form one helium atom, and a whole lot of energy gets released. And as soon as the nuclear fusion starts, then the protostar, or the beginning first star there, begins to glow. Now, how much dust and gas was swirling and squeezed together will determine what kind of star it's going to become. And as far as we can tell, the theory goes that stars have a predictable life cycle. So no matter what size the star is, they all start off in a nebula as something called a protostar. So that's why you have 3 of these in a row. And again, you get the swirling dust and gas, and it condenses down, squeezes, high temperature, high pressure, all that, squeezes together, ignites, and then the hydrogen starts to turn to helium. If it doesn't have a lot of that hydrogen, then what will happen is it'll grow up, it'll swell as it begins to get older, and it will become a red dwarf, quite a small star in comparison. The red dwarf then will begin to cool, and as it begins to run out of hydrogen energy, and there's only helium left, only the helium is left to burn, and it will eventually die out as a white dwarf and then become a black dwarf. If it's a medium mass star, something like what our sun would be, it has enough hydrogen at the very beginning to fuse a lot of helium. And that helium then will then be able to fuse itself together to become other types of elements. Eventually, after it's lived its billions of years, it will begin to swell. It becomes something called a red giant, and then it will shrink down to a white dwarf and eventually a black dwarf as well. If it's a massive star, way larger than our sun, then as a protostar, it's got a ton of hydrogen. It burns very quickly because it has so much gravity that the pressure and the temperature on the inside of that star fuses and burns through the hydrogen fuel much faster. And so when it begins to age, it actually swells up into something called a supergiant. And then it explodes in something called a supernova. So it'll be it'll throw off its outside shell, and the final result, depending on the size of the supergiant, the large but not largest supergiants will become neutron stars, and then the biggest of all the supergiants, when they explode, they become something called a black hole. It's thought that when the stars shed their outside in a supernova, that might be what causes the nebula gas. So then you would have this being the fresh start of a new nebula that can then be the birthplace of new stars. Let's look at more of the details. So here we are then looking at the lowest mass stars. These ones are the ones that will be red when they are mature. And remember that all stars are going to begin as the protostars. Now they're going to use fuel a lot slower because they are smaller. There's less gravity. That means there's less temperature and pressure to ignite the hydrogen. So they burn through their hydrogen fuel a lot slower. So they think that maybe there's enough fuel for these guys to burn for 100 billion years. That is quite a long time. And because the nuclear reactions are happening at a slow rate, they actually shine very weakly. So these are very dim stars, and they will be red dwarfs at maturity. When they run out of fuel, they collapse under their own gravity. So they've swollen a little bit to become a red dwarf, but then they're going to collapse, and then they will cool down into a white dwarf. And a white dwarf is made of helium. Remember that we're going to be taking hydrogen, We're going to be fusing it together to become helium. Now, there's not enough helium then to reignite and to fuse into larger elements. So this will be the end of the line for a low mass star. And when the white dwarf runs out of helium, it'll turn into a black dwarf. A larger star, something like our sun, we would consider a medium mass star. We have a yellow medium mass star as our sun. They're going to burn fuel a lot faster. Again, because they're larger, they're going to have more pressure and more temperature. That means that they'll burn through their hydrogen. Even though they have more hydrogen, they'll burn it faster and maybe only 10 billion years. When the hydrogen fuel runs out, in this case, the star collapses just like the red dwarf did. But when it collapses, it actually squeezes, raises the pressure, and that raises the temperature, and that actually starts the fusion of helium, and helium being added to other helium atoms, which will then create larger and larger elements like carbon and oxygen. And when that happens, you get the fusion of helium, you get all that release of energy, the star reignites. As the core heats up, that star will quickly expand into something called a red giant. Keep in mind, when we say quickly, we still mean over billions of years. They will expand into a red giant, and then eventually the helium burns out, the star collapses again into a white dwarf, and then finally burns out, becomes a black dwarf. There's some pretty famous examples of red giants. Aldebaran and Betelgeuse are two examples of those. Now, if you are 1 to 4 times, so either the same size as our sun or 4 times the size of our sun, you will likely be able to, as a star, create helium from the hydrogen that you started with. Then you can probably produce carbon and even some oxygen. If you are larger than 4 times, then not only are you doing helium, carbon, and oxygen, but you might also be creating silicon as well, as a much heavier element inside that particular star. Now, keep in mind that carbon is the same atoms that diamonds are made of. So when they are under a lot of pressure, the carbon forms diamonds, which is very cool. High mass stars then are stars that we would consider to be at least 10 times the mass of our sun. They are hotter, they are much brighter, they are bluer, and they have a much shorter lifespan because they burn through their fuel. Even though they have a lot more fuel, they're going to ignite it much quicker, again, because they have so much temperature and pressure that the hydrogen fuel gets used up quite quickly. They will collapse just like a low or medium star will, but the difference is when they have that heating and compression and they start the helium fusion, they expand into a supergiant. These are the biggest stars that we have out there, a super red giant. Now they are approximately 1.6 billion kilometers in diameter, which is about the size of Jupiter's orbit around our sun. So if our sun had been a larger star, when it became a supergiant, it would have consumed the first 4 planets, Mercury, Venus, Earth, Mars. It would have consumed the asteroid belt, and it would have reached all the way out to Jupiter. Thankfully, ours is not that large. Eventually, the helium fuel runs out, and the star collapses again. In this case, though, because it is so large, not only have they been able to form, the hydrogen forms the helium, helium becomes carbon, carbon squishes to oxygen along with these other elements, they form silicon, we can form iron. As soon as you form iron at its core, it actually takes more energy to produce the iron than what is released by fusing that iron. So that actually begins the beginning of the end of a star. Now, the reason I've got it laid out like this is I want you to imagine that this is the core of the star, the very inside, the most dense, heaviest element in the middle. And then if you can imagine the silicon as a layer, oxygen as another layer, carbon, helium, and then finally hydrogen on the outside. Okay? So these layers are arranged by their density, with the heaviest or most dense element at the core and then moving outwards to the lightest element. When a very high mass star comes to the end of its life, there are 2 pathways that it can take. But both of those pathways go through something called the supernova, which is the massive explosion. This is going to occur only if you have a lot of iron. And again, that's because the iron itself takes so much energy that it actually sucks the energy from the rest of the star so that the star actually turns off. it is no longer producing more energy than it's using. When it turns off, it actually collapses. So you've gone from this huge red supergiant and it shrinks right down. Well, that shrinking is going to cause an increase in pressure again, which causes an increase in temperature. It heats up to a ridiculous temperature, millions and millions of degrees, and that's going to cause a final explosion, so spreading outwards in all directions, and then a final implosion. And it's this implosion where it comes rushing all back in that you end up forming either a neutron star or a black hole. A neutron star would be produced if you have a high mass star, so about 40 times the mass of our sun at max, but it squishes down. This implosion comes down so tight that it is only about 15 kilometers long. That's the width of Barrie, Ontario. It's not very wide at all. So you can imagine a huge massive star being squished down into a very tiny area. And it is made of the densest material that we know of, literally made of neutrons. No protons, no electrons, just neutrons. In fact, they estimate that 1 tablespoon of this star, it would probably weigh somewhere around 10 million tons, which, for reference sake, is about 1,333,333 elephants being squished down into 1 tablespoon. Crazy. Now, that's not even the largest stars. The very high mass stars, things that are more than 40 times the mass of the sun, after they go through a supernova and explode, they have so much pressure that when it collapses, it becomes extremely small. So this implosion step becomes so very, very small, but it's all of this mass in a super tiny area that makes it very dense. This huge density then creates an intense gravity. The gravity is so strong that it not only sucks in matter, but it actually sucks in light and even can bend time. The more the black hole sucks in, the bigger it gets. Let's take a quick look at this short documentary to give you a better visual of what we've been talking about.
Nebulas house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter. Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core, and when they do, they heat up. They can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
human lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another. Here and there are even more brilliant flashes of light, coming from some of the most violent and dangerous neighborhoods in the entire Milky Way galaxy. Here, stars aren't born, they die.
So one last time, stars start off in a nebula as a protostar because of the spinning of the dust, and it begins to ignite the hydrogen fuel. The smallest mass stars will live their lives as a red dwarf and then eventually shrink down to a white dwarf and a black dwarf. A medium-sized star like our sun will glow either as a yellow or maybe a more whitish, depending if it's a little bit larger than our sun. It'll expand to a red giant and collapse down again to a white dwarf and then to a black dwarf. The largest of the stars, with so much of that hydrogen, will burn very quickly. They're going to expand through their life, become a supergiant, explode as a supernova, and then either become a neutron star or a black hole. So now that we know the different types of stars that are out there, red dwarfs, white dwarfs, black dwarfs, red giants, supernovas, supergiants, all sorts of stars, let's take a look at where they fall on something called the Hertzsprung-Russell diagram. Now, the Hertzsprung-Russell diagram has just taken the stars that we can see and it has laid them out in a logical pattern. They've compared the color of the stars. So you have your reds, you have your yellowy whites and your blues. They compared the color. They compared the brightness of them, or the luminosity. So the dimmest stars are at the bottom and the brightest stars are lined up along the top. And then the third thing that they looked at was the temperature of the star. Now, one thing you need to notice about this particular graph is that the temperature is in an odd direction. In fact, the hottest are actually on the left and the coolest stars are on the right. Let's take a quick look at this video and I'll show you how they put together the Hertzsprung-Russell diagram.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When their fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So again, on the Hertzsprung-Russell, stars are sorted according to their color, their luminosity, and the surface temperature. And then the main sequence stars are stars that are in the main portion of their life, and the band that would go from the top left to the bottom right. Any group that is not on the main sequence is dying or near the end of their life. So let's take a look at it one more time. So here we have our sun. We can expect our sun as a medium mass star to swell to a red giant and then become a white dwarf. These red ones down here will likely just end up as white dwarfs. These larger blue over here will probably become supergiants and then explode out and either become black hole or a neutron star, again, depending on how massive it is. Just a couple extra little facts. White dwarfs are extremely hot, and they are dim because they are very small, and they will eventually turn black. The red giants, on the other hand, what our sun will become, the outer layers are actually a lot cooler, and they're bright just because they're so large, and these guys will eventually explode. And that, my friends, is the end of this lesson.